great to be among so many distinguished colleagues and professors. My name is Ziad Shahata, and I'm coming from the Zuwail City of Science and Technology, the Department of Nanophysics. And today I'm going to talk about the quantum information science and how can we process information in the quantum world using this order. And I'm going to study both the systems of quantum information in terms of quantum circuits and also in the model of quantum optics intertwined with quantum many-body systems. So arguably the challenges of physics outside of physical sciences, the frontiers of physical sciences, are going to be like this. And we have ultimate control over detecting waves, recent Nobel Prize in Physics, the gravitational waves and variable also in Europe. And also for the short distance, we go from long distance to short distance, we have the detection of the Higgs boson, which got the Nobel Prize 2012. We have some interest in quantum gravity, supersymmetry. People in high energy physics are going to be related to this topic. But for our interest in the quantum world is the complexity. We would like to study entanglement, we would like to study correlation dynamics, different unitary operators, maybe non-unitary operators, isometry, and so on, which is going to be useful for a universal quantum computer. How can we build simulation of everything? I would say the quantum circuit model. So we're going to just remember quickly that nature is not classical, damn it. Nature is probably quantum mechanical, and to make a better simulation of nature, it's better to make it quantum mechanical if we'd like to study quantum systems. So this was the start talk by Richard Feynman. He envisioned both the nanosystems, there is plenty of room at the bottom, and also how can you build machines which are very tiny using quantum systems, quantum machines. And he envisioned that you have to make them very small, and he meant very small. So let's begin with the birth of quantum information quickly. We're going to mix the quantum theory with the information science. We have bits and we have spins, quantum theory, and by then, thereby you can look at the quantum information perspective of the superposition state of different spatial configurations of the atomic system, for example. And you can build a superposed entangled state, coherent entangled state, like this diagram. And that's just write down our usual wave function, which is going to be a simultaneous superposition state between different spatial configurations, which is going to expand, or we can call it extend the Hilbert space, the state space of the system. This is, infinitely large scale dynamics, all of this. Specifically, when we would like to couple the atomic system with the radiation field mode, which is also a harmonic oscillator. It's a quantum harmonic oscillator. And we would like to talk about the dynamics, we would like to talk about the couplings. The many-body processing is going to be like this, just the throttle expansion. We're going to have some spins, load spins at the initial state, and we're going to evolve it over time. And by then, you can just write down the unitary evolution of the exponentiating the Hamiltonian, which is going to be throttle expansion. And we would like also to get some errors, because errors are fundamental of this thing. Which is going also, we can write down the effective Hamiltonian of the system. And yes, we know that all the quantum circuits, the gates that we can process, different Toffoli, Hodma, whatever. And by this way, we can write down the equations for coupling of the radiation fields and the atom. We have control bits, and we have the target, the atom. We call it non-destructive measurement of the photon, or maybe the atom. We're just processing in the cavity. And by this way, we can write down the, we call it dressed state of the system, the dressed atom picture, light and atom, and which is going to be like this. We can have single photon, maybe one